This is actually a joint talk given by not only Ricardo and me, but also of several co-workers actually doing the real stuff. And unfortunately, Paul couldn't make it, but his part will actually be supported by his co-worker, Michel. Yeah, again, welcome. Yeah, task area 5, use cases. This is the topic. And we are going to present several ideas, perspectives, and technical issues, particularly then later for discussion, that are about so-called blind prediction challenges that we identified as a reasonable and useful use case for NFDI4Chem, particularly for task area 5. And as said, this will be a joint talk, and the presenters here will be Ricardo, Michel, and Nicolas, and myself. Starting out, as the motivation for this whole work, a few years ago, exactly 2 years ago, this paper actually stirred quite some excitement in the community. This was basically a landmark paper or comment, actually, it was it, in Nature Methods by Casey Green's and Stephanie Hicks groups. Reproducibility standards for machine learning in the life sciences. And the ideas behind that paper are not really restricted to life sciences and actually not really to machine learning, but the key information is basically given here in this box. Ultimately, all science requires trust. No scientist can reproduce the results from every paper they read. The question then is how to ensure that machine learning analyses in the life sciences can be trusted. And that is actually the topic, trust. And for trusting things, of course, many things have to be provided to the community. And this paper then identified a number of key features that they classified in terms of several standards, the so-called bronze, silver, and the gold standard. And the gold standard ultimately means that besides these earlier points like data publishing and downloadability, of course, in the end, everything should be reproducible by hitting a single key. That is, the ideal, in an ideal scientific world, an entire paper or any kind of report should be reproducible or actually, doable by simply hitting a key that enters a script, and this script should actually produce all figures, all tables, and in the long run, with artificial intelligence, even provides the text for actually producing scientific insight in forms of data collection plus the corresponding discussion of the results. And that is actually unachievable, at least for, I would say 99% of all published work. This is basically not possible. So even the bronze standard is something that is at least a goal that we could like to achieve or would like to achieve, but even that is problematic. So for instance, data publishing, downloadability, that means accessibility in terms of the FAIR standards, is of course necessary. Publishing models is of course also desirable, and even the third ingredient of this bronze standard might be problematic. For instance, publishing all the source code and make it downloadable and available is not always possible, simply because of many groups use proprietary software. They have restricted licenses, and that makes it actually, even at this easy quote unquote level of the bronze standard, even a tough goal to achieve. Now the idea before handing over to Ricardo is to include everything in terms of a test bed that we defined as so-called prediction challenges. And now Ricardo will give an overview of all the prediction challenges that have been around.
So by prediction challenges or blind challenges, we mean that there's a published data, there's data available which has to be reproduced by some theoretical models. So we're focusing on blind challenges for theoretical models. And the theoreticians involved in that prediction are unaware of what is the target experimental value. This is something that has been tried to be established in several ways in the community to eliminate bias when there's simulations modeling involved. There's many entities involved in this. One is the Cambridge Crystallographic Database, which has been promoting structured prediction tests. We also have in our research training group in Göttingen a bench proposed gas phase challenges. These are mostly geared towards academics. I will talk later about some of these. And also the sample challenge, one of the most long-running challenges in the theoretical chemistry or in general modeling community, which focuses on sufficient free energies, binding of different large molecules with pharmaceutical interest. And these, both the gas phase challenges and as well as sample, offer a platform for a wide variety of theoretical methods so that all of these can be very critically tested and compared in an unbiased way. This involves not just academic partners, but also industry. And in the future, we want to involve these different attempts in a larger framework, more encompassing through the national research data infrastructure, push the community for certain standards when it comes to research data management, because this involves a very active exchange of data, not only from the side of the organizers, but also the people submitting their predictions. And ultimately, after all work is done on the challenge, we can actually recycle all of this data for future benchmarks, which, as Stefan proposed or hinted at, ideally in one case, one would be able, if one develops a new simulation method, with a click of a button to try it out with established benchmarks, which were established perhaps 10, 20 years ago. In the next slide, I present you one of these first challenges that we in Göttingen propose. It's a very simple question. If we have furan and methanol in the gas phase, how will methanol bind to the furan molecule? Is it an OHO binding? Will it sit on top of the ring? We had a group, 9 participating groups on this challenge, who sent their predictions not only for furan, but also for different degrees of methylation. With increased methylation, the OH pi conformation gains a little bit more weight, and we analyzed this through infrared spectroscopy in order to predict experimentally what would be the preferred conformation. This might seem like a small question of 3 data points, but in the next slide, we see that there's a possibility of evaluating theoretical models in many, many different perspectives, many different parts of the calculations themselves, not just one single data point to be compared in the end, so that we can critically analyze. These letters stand for submissions. We can critically analyze which computation protocols have the biggest promise, which are most robust for these types of calculations. Now, how is this all organized? Well, first thing is, of course, to identify a system, identify a question. We have to have a control tactic, meaning that we have to have some perimeter, which we will vary. Mostly it's the chemical composition, which molecules we are including in the challenge. And then we have to evaluate the experiment in a way that we know that we're comparing apples to apples, and that we are able to say to anybody in the community, well, if you try to calculate this value, we can have an experimental prediction to this. It's not as simple as just doing one experiment. Well, oftentimes we find that we should do complementary experiments to really nail down this value, to be really sure. For example, if we want structure in the gas phase, it becomes important not just to have infrared spectroscopy involved, but microwave spectroscopy. And after all this is done, we have the challenge, the comparison to furan, and after this, after all the experimental work and the theory work from the community, we can develop the stable and robust benchmark that can be used for a long, long time, doing away with working with just references from coupled cluster theory, testing theory, or eliminating certain chemical bias. In the next slides, we see some of the newest challenges we've been proposing. In this case, it's the Hydro Challenge, which was put out in 2021. The question now was to predict the redshift of the OH stretching frequency in water when it forms a complex with an organic molecule. We can do this for several different organic molecules. Through jet expansion, we can measure the infrared signal of the OH stretching frequency, and then independence of the molecules involved have a value that can be compared to furan. In the next slide, we see that we were working with 10 training systems, which were provided before the challenge was started. So the groups had a few months to test out their methods. And then at a given date, which we, of course, announced, the test systems were provided, their names were given, and then the theory groups had about 3 to 4 months to submit their predictions. In the next slide, we see a different challenge, still in the gas phase, but now in kinetics. Transmetallation reaction, which was studied in the Kozinovsky group. We had a few examples before done by the same group where one tested the experimental approach, one knew through mass spectrometry in the case of zinc complexes, had a good comparison to careful calculations done before. Now one moved to a more demanding system, iron complexes, and had an announced period for the groups to submit their predictions. And these were all, the communication was all supported by an online platform, qmbench.net, where the online forms were provided for people to submit their data and then for the results of the challenge to be published. In the next slide, we see some examples, some snapshots of what we have in the website. After the challenges are done, or even before that, we're trying to put up data that can be reliably compared to simulations. In this case, we see a simple plot comparing experimental wave numbers for a selection of OH stretches in different dimers and comparing it to the theoretical values, in this case, Beckford Lip, where we can basically see how well the theory performs. With one click of a button, we can see how this, in terms of the absolute or the relative wave number, how things change. If one selects one of these entries, we see in the next slide, it can be provided information about the actual spectrum which was used to derive that value, and also look at the microstructure which is proposed to be the microstructure responsible for that signal, and everything is downloadable so that every theoretician can try for himself or herself to calculate these values and compare to well-curated experimental data. Moving forward.
Yeah, and the sample challenges are, as Ricardo said, is basically devoted to problems now in solution. So sample stands for statistical assessment of the modeling of proteins and ligands. The key organizer in the past years, at least, was actually David Mobley. So he's, well, the colleague who actually took all the burden to organize several of these challenges starting several years ago. David Mobley from UC Irvine is now basically at the end of his funding period. And so the idea was then later to, well, basically continue in close collaboration with David, of course, the idea of these sample challenges. So historically, sample started out, more than 15 years ago, with a focus on one of the key properties in solution chemistry, and that are free energies of solvation, and more specifically, hydration free energies. Because at that time, this was basically the key benchmark quantity to be able to predict in order to test force fields, in order to test molecular simulation protocols and quantum chemical approaches to that. So later it extended its scope, for instance, even in 2009, the first example for solution phase properties like reaction-free energies was part of the challenge, in that case, tautomerization-free energies. And then in 2011, basically the addition of host-guest equilibria started in close collaboration with the so-called D3R, the drug design data resource by Michael Gilson at the UC SD. And these so-called grand challenges were about, predicting protein-ligand structures, binding modes, binding affinities. And these worked in close collaboration then with later sample challenges on these host-guest binding properties. And then in 2050, actually the shift there was a shift going further to other solution phase properties of small molecules of pharmaceutical relevance. So not only hydration-free energies were relevant, but properties like acidity constants like a pKa, partition constants like a log P, and distribution coefficients like a log D. And that was also then the topic for the later challenges, sample 6 through 9. So what is that actually? A log P is essentially the partitioning of a compound between water and an immiscible organic phase. For instance, you might well know the famous log P octanol water as a mimic for lipid transfer of pharmaceutical compounds. And that actually requires that one is able to predict the free energy, the solvation free energy, or the chemical potential of all compounds in the different phases in water and, for instance, the organic phase. And from that, you can compute the transfer free energy, and from which you obtain basically the equilibrium constant, the P. So if compounds can be protonated, deprotonated, then it becomes a coupled problem of partitioning and protonation, and these quantities are then called log D, the distribution coefficients, that actually measure the total amount of protonated and deprotonated species amounts in the two different phases. And actually this is the real key challenge, because the overall accuracy that one can obtain is not better than between 1 and 2 log units. And that means these log D challenges are really, really, really tough challenges. So in the end, what this is all about is to make a prediction in the sense of, here is, for instance, the experimental quantity, and here is the calculated quantity. And in an ideal world, all these data points would lie exactly on the main diagonal. And different models are actually capable of different predictive capabilities. And these predictive capabilities actually are a measure, and a more or less unbiased measure, depending on the quality of the experimental data set, of course, of the prediction. And you can therefore test models, and that is basically the added value to the community. So one of the key problems in sample challenges is the broad variety of methods. So whenever it comes to problems in solution, you can work with atomistic models like explicit molecular dynamic simulations, with force fields, or even with ab initio. You can go to the upper end here by replacing the solvent completely by a continuum, so-called dielectric continuum models, or there are other models in between, like statistical models on the basis of integral equation theory. And of course, nowadays, becoming more and more prominent are models based on machine learning or on rules. And these models have the potential to essentially be better than atomistic models, as long as the reference data is broadly available and in large amounts of high quality. And from the solute description side, of course, we can use any kinds of, from force fields up to high-level quantum mechanical descriptions. And that means the whole bunch of models, from machine learning up to full quantum mechanics coupled to molecular dynamic simulations, is the real challenge for actually handling the data and combine that with the experimental reference in order to really make these models reproducible. So the next thing is, of course, then starting over what actually David Mobley presented early on, and put it to the next level by combining it with the ideas of research data management, particularly in the form of the NFDI compliance. And that means we had to decide early on which kind of new models we want to treat and new areas we want to treat. And we decided that it makes sense to focus again on the pKa prediction problem, the acidity constant prediction problem, and basically give it a new spin that makes it attractive for groups working in that field to combine that with research data management. And Michel will present more details on the experimental side here.
Yes, thank you very much. The generation of the experimental data, which are used for the sample challenges, is executed by the Czotowski group at JGU Mainz, which I'm going to represent today. And we are using the industry standard device for pKa measurements, which is called the ZeroT3. And it can detect the UV absorption of the protonated and deprotonated species of our compounds. But I will show more details about this on the next slides. Before doing so, I would like to give you some additional information about the molecular compositions. My predecessor, Juliana, which you can see on the top right, measured almost 40 compounds with the device I just mentioned. And together with Nicolas, she worked heavily on the tautomer enumeration to unambiguously assign the preferred tautomeric substate. And additionally, Nico also ran some high-level QM calculations. In the end, all the measured data together with the computational work was combined to allow a fair data composition and eventually a fair data submissions as well. We additionally also try to implement the gold standard of reproducibility by implementing a containerization of the data, but more you will hear about this on the next slides. Now I want to show you how we measure the pKa values. The 053 measures the pKa values by measuring the absorption, and it does doing so by using a UV matrix pKa determination. And we try different concentrations of our compounds, and we're able to observe the deprotonation reaction by looking at the absorption spectra. The only requirement for this method is that you have to have an UV active site in the system, which is maximum 3 bonds away from the titrational group. After we determined the concentration of the deprotonated and protonated states, we were able to fit the absorbance data to a theoretical molecule. And in the end, we were able to estimate the number of pKa's by using the Lambert-Beer law. I have to say, unfortunately, we are bound to use the software which is provided by the EOST3 and have to review every measurements by hand. And also we have to compare the measured values to a theoretical value predicted by Marvin. And also, of course, we have to check if the compounds have been measured in the literature before. So they have never measured before. And if we are sure of that, we can export the data as a CSV and use it for the upcoming sample challenges.
Okay, and then the technical stage comes in terms of how to organize everything that the participants of the challenge will actually provide in terms of materials, methods, data. So coming with the background of this wide variety and diversity of methods, we first had to make a decision on what kind of data is the primary data and what kind of data will be related data that is essential for actually measuring something like a fairness score in terms of how compliant with established research data management conditions are the submissions. So in the end, all submitters have, of course, provide their final pKa values. And as usual, they have to provide the full methodical documentation. I mean, that is state of the art as it was before the old days, before then research data management standards gained more importance. For properties like a pKa that is actually derived in a sense of microscopic models from preliminary data coming from, for instance, QM or MD simulations, it means that the demand in order to reproduce such a single number is very high and derives actually from raw data like microstate energies and the complete workflow, how to assemble all these data in order to end up with a data point like a pKa value. And that means a lot of things have to be done in the middle, and that means starting from, for instance, a SMILE string as the initial entry point that the participants actually obtain in order to make their predictions. Typically, users have to do a lot of steps in between before making actually the final submission of the final data point of the target property. Whereas, for instance, machine learning groups will not have the demand to use all these things, but come directly from the SMILE strings, for instance, and end up directly with the target property without any kind of intermediate microscopic data. And that means we cannot easily assemble all these aspects under one common umbrella. Besides, actually, at least demanding from everybody who is using all these microstate energies, for instance, to provide their workflows and their standardized script-based evaluation in order to make it possible that everybody can assign the fairness score to their peers. And that means the idea is that each group actually evaluates the fairness of all other submissions, and then the overall score will not only be the pure metric in terms of quantitative agreement with the experiment, but also in terms of agreement with the research data management policy. And that is actually the new aspect of this Eurosample challenge, in order to, as Ricardo said, to push the community actually to adopt the standards. And that means to be as complete as possible in terms of reproducibility with solid and sound research data management will be the key to success in this challenge. So as an example how it could look like, this is what we are planning very soon to publish as our own results in the sample 8 prediction challenge. And that was about predicting pKa, log P and log D for a variety of organic solvents plus water. We as a working group actually do atomistic calculation. That it means we have the energies of all compounds in water, in the organic solvents, starting from the optimal structures in the respective environments, from which we compute all these target properties. And that means all the raw data that will turn out during these runs will actually be part of the supporting information in complete machine readable format, and planned to be available in a way that from the raw data, like here, this tabular data, everybody else in the field will be able actually to produce not only the final outcomes, that is the final target data, like log P, log D, and pKa, but also from the scripts automatically to generate all tables and figures automatically. So we are actually getting close to a standard that, for instance, Chemotion has already set out to be able to, to generate supporting informations coming from an electronic lab notebook. But as the Chemotion, for instance, as a lab notebook is not the perfect object to work with in these heterogeneous experimental and computational environments, we are at least taking that as a role model to approach this standard as close as possible. And that means in the end, we came up with a technical solution that we are currently building up and that is close to finishing, and that will be presented in more detail now by Nicolas.
Yes, so for our Eurosample challenge, we chose to have two main entry points. The first one is the QMbench website that we already saw earlier in the talk, which is hosted in Göttingen. Or the participants, if they can find it directly, can also go on the GitLab, and there they get the three main things that they need to start working on the challenge. For once, the list of compounds as basically the SMILES format and a name with which they can refer to it. Then the challenge instructions and the submission templates for both the metadata and the pKa submission. And once they start their work on that, they can then do that until a certain deadline, and then they have to submit their data. So this data submission happens in three parts. First, they, according to our template, can submit the metadata, and this is not just the citation metadata, but also their workflow-specific metadata. And because we have such a heterogeneous environment of different tools and potential programs that they use, we didn't actually give them any template for the second part, so they only have required metadata for the citation metadata, but all the other specific to their workflow metadata should be suggested by them and then also evaluated by other people who use those same programs. Can I actually reproduce those calculations using just the data they supplied? So this is automatically checked, at least the required metadata, and then used to generate a submission ID. So one single work group can also conduct multiple submissions. However, only one of those is ranked, and that is all contained in the submission ID. Once that is done, they can upload the second template file, which is just their pKa prediction. This is also in a fixed format, which is then automatically analyzed using a Python tool. And we also, basically upon the successful upload, we generate the statistics. Some of the figures you already saw at the last slide, at least as that's sort of the template that we use for that. However, this is of course then not directly publicized, but this only happens after the challenge deadline. Finally, the research data part is kind of optional in how far these participants can go. So obviously, ideally, they would supply us with an archive where you only have to press one button and the full analysis is done. As you could see in the gold standard, however, that is not realistic. What we hope that we get is basically some of the energies, the input files for some calculations, maybe even an analysis script that you can run that takes the energies and generates the pKa prediction file. That would be very nice to see. However, the participants have a lot of leeway in what they actually send us here. However, it is then evaluated by their peers. So we hope that this serves as sort of motivation to make it as good as possible. Finally, this is then all put in this submission folder and uploaded to our GitLab instance. And there two things happen. For the first part is obviously the most important part, taking all the submissions and giving them to one another so they can be evaluated according to their FAIR score. And the second part is that we then publicize the data in our Dataverse, and this is all happening on the infrastructure that we have at the TU Dortmund University.
So the question comes then, what are the next steps for the Eurosample challenge? That's pretty well defined. It's going to start in late summer. In autumn, we hope then to close up the store, to have the evaluation of the results coming in. The structure is, for the most part, prepared, gathering around the joint technological platform at the TU Dortmund, connecting GitLab to Dataverse. The landing page is provided by the QM Bench website in Göttingen. The way to go about this will be to have a joint publication of results. That's the formula we've been using previously in other challenges. I think it's also a nice way, a nice incentive for all the groups participating to have a really strong, impactful paper instead of breaking it up into single parts. We will plan to extend, of course, the different challenges to encompass more molecules, diverse in terms of properties, and build up on what has been done in the past few years. And I would like to call also the attention to the dedicated Eurosample session then on the 18th German Conference of Cheminformatics next year in November. Now comes a part which I think is very pertinent for the discussion after the talk, is what's the perspective in terms of synergies and collaborations within the NFDI4Chem. The question of data submission processing is a quite live one, how to improve on the workflow in these different parts that were presented, more particular for the Eurosample challenge, integrating experimental and computational repositories, ELNs. These are all points that touch on other task areas. The ELN question also goes into the point where we could have an automated SI generation so that in these challenges, we can have the participating groups having the minimal amount of work in preparing things by hand, that we have an SI which is collated from the different contributions. Maximizing reproducibility by these complete workflows is something we would like to do, but if there's experience in something related that we can build upon or adapt to our specific needs, that would be great. And of course, the general workflow integration with the ELNs task, which is clearly for TA2, but where we see that there's a lot of perspectives, different perspectives in going forward. In short, I think we are catching onto something which is very valued by the community. We have very good feedback from previous events. A lot of people with interest in participating in future challenges and gathering more momentum with each challenge we make. We see a doubling of participations in some of these challenges. And also we have a clear path, not based on the stick, but on the carrot to get groups involved in new practice and new level of research data management in chemistry. And with that, I would like to move over to the discussion, and I will be very happy to hear about your ideas in integrating into other initiatives and work being developed within the NFDI4Chem.